All right, so chapter 2A, we're on 2.2 day 1, which is polynomial functions. So go ahead and pause the video, try the warm-up here, which is describe the end behavior and limit notation from last chapter. Okay, so whenever you're writing end behavior and limit notation, remember you have the limit as x approaches negative infinity of the function. The function doesn't have a name, so let's call it f of x. Of f of x is. So now we're saying as our x values get smaller, what's happening to our y values? So as we look this way, you can see your y values are getting bigger. So I'm going to say they're approaching infinity. And then the limit as x approaches infinity of my function f of x is. So as I'm looking right, what are happening to my y values? They're leveling off at what y value? 2. Okay, so first off, before we talk about the attributes of a polynomial function, we have to talk about what a polynomial function is. It says it's in the form of, and then it gives you this terrifying looking thing and just a bunch of information. It's so I'm just going to go ahead and fast forward through that and show you that here we have polynomial functions. This is what polynomial functions look like. So if you look at these, there's terms separated by a multiplication and division. And then the rules for it in order to be a polynomial function is that the coefficients have to be real numbers. So like these have to be real numbers here, which these are. But like root 3 is a real number. It just can't have I in it, right? And then the exponents have to be whole numbers greater than 0, right? So you're counting numbers plus 0. So 0, 1, 2, 3, 4, so on and so forth. So you can't have negative exponents, basically. Okay, so that's what a polynomial is. First thing we're going to talk about is the end behavior. So it says, in lesson 1.3, you learned that the end behavior of a function describes how the function behaves, rising or falling at either end of its graph. So as x approaches negative infinity and x approaches positive infinity, the end behavior of a polynomial function is determined by its leading term. So we are going to use what's called the leading term test, which uses the power and the coefficients of this term to determine the polynomial end behavior. So first off, it has to be written in standard form. So if you had a polynomial function that was written p of x, let's call it, equals, and then it was 2x squared minus 3x cubed plus 2x to the fourth minus 6. You would have to rewrite this so that your highest exponent came first. Okay. So let's talk about each one of these. We're going to talk about an odd degree function with the lead coefficient positive, an even degree function with the lead coefficient positive. So now when we're talking about even and odd, this time we're talking about the degree, okay? So we're going to give an example also of each one where it says f of x right here. Okay, so we need an odd degree, so that would be like 1, 3, 5, 7, 9. So we're going to use x cubed, let's say. And then a lead coefficient that's positive, so I'll use the number 2. So if your first term was or your leading term was a 2x cubed, think about what x cubed looks like, and then think about a positive sloped line. So this is what a 2x cubed would look like, right? So if you notice this, you're going to have your arrows pointing in opposite directions, like a positive slope line if you were to make it taut. And the limit as x approaches negative infinity is negative infinity. Limit as x approaches positive infinity is positive infinity. Let's go right underneath that and do the odd degree function with lead coefficient negative. So odd degree, let's use x cubed again. Let's do negative 2x cubed. So remember, all that's going to happen here is a vertical reflection. So this would look like this. So your arrows are still going to be pointing in the opposite direction, but if you made this taut, it'd be like a negative slope line. So as x approaches negative infinity, the slope is positive infinity. And as x approaches positive infinity, the function is approaching negative infinity, the y values. All right, even degree functions with lead coefficients that are positive. So even degree would be an even exponent, 2, 4, 6, 8, 10, and this is your lead term. So let's do x squared. and then a positive lead coefficient. Let's do 2 again. So quadratic would look something like this, right? So arrows are pointing in the same direction, both pointing upward because that positive 2 in front. So the limit as x approaches negative infinity is infinity. The limit as x approaches positive infinity is infinity. Last but not least, we have an even degree, so we'll say x squared, and then negative lead coefficients. We'll do negative 2. That would look like this. So this is going to be negative infinity, negative infinity. Okay, so once again, I kind of did skip over saying that part right there, which was important. The greatest exponent is what we're talking about when we're talking about degree. Okay, so to summarize this, your first term, your leading term, is going to tell you whether your arrows are pointing in the same direction or opposite direction. So if it's an odd degree, then it's opposite direction, same degree, even degree, same direction. Now, if it's an odd degree and there's a positive lead coefficient, it's opposite direction and like a positive slope line. If it's negative lead coefficient, it'd be like a negative slope line if it was a line, if you pulled it taut. And then even degree, that's going to be the same direction. If it has a positive lead coefficient, they're both pointing up, negative, both pointing down. So let's see if we got it here. Describe the end behavior of each polynomial function. So first off, I have to find the first term. If it was written in standard form, that's this term. So if you look here, this is an even degree with a positive lead coefficient. So even degree would be in the same direction. Positive would be that the both arrows are pointing up. So this is how the ends of my graph look. Now, in between there, like it could look like this for all. It doesn't matter what the in-between is. We care about the ends right now. All right. So now we're going to say what our end behavior is. We're going to say the limit as x approaches negative infinity of my function, which this is called f of x, is. So as you look left, you can see that your values are getting bigger. Limit as x approaches positive infinity of my function, which this is f of x, is. And as you look right, you can see that my y values are also increasing here. Okay? All right, so I'm going to save myself some time, and I'm going to do a little copy-paste action again. Copy, copy, paste, and then I'll just delete what I don't need. Boom. This is not called f. Okay, so looking at the next one here, I look for my first term. It is in standard form once again, so this is my first term. This time I have an even degree but a negative lead coefficient, so I know my ends are pointing in the same direction, but they're both pointing down. So this is going to be the limit as x approaches negative infinity of g of x is negative infinity. The limit as x approaches positive infinity of g of x is negative infinity. All right, I'm going to paste again. Can I paste again? Let's see. Paste. Ooh, look at that. All right, I'm going to delete once again what I am going to be changing here, the name and what it's approaching. All right, so the limit as x approaches negative infinity of h of x, and this is h of x here. Okay, so now I'm going to look at my first term, 4x cubed. So cube is an odd number, odd degree, opposite directions. 4 is positive, so they're pointing in the opposite direction. But if I were to connect these with a taut line, it'd be like a positive slope line. So as my x values get smaller, my y values are getting smaller, and as my x values get bigger, my y values are getting bigger. All right, so last one, paste here, change what I need to change. Okay, this is j of x and j of x. All right, what does this one look like? So here's our first term, and it's in standard form, so it's our leading term. I have an odd degree, so opposite direction arrows, but this time it's -3, so it'd be like a negative slope line. So this would be connected, and it might look like something like that even. Well, that doesn't really look like a function, but it might look like, you know, like this, okay? But if I were to pull it taut, it'd look like a negative slope line. So the limit as x approaches negative infinity is positive infinity, and the limit as x approaches positive infinity is negative infinity. Okay. So now what we're going to do is we're going to learn how to graph a polynomial function, So when you're graphing a polynomial function, all of these things are going to be asked before you graph it. Okay, so what we're going to do is we're going to learn how to get all of those things first, And then the next set of notes, the day 2 of notes, is where we're just taking all of that and actually doing all of this, but then just graphing it, also putting it on graph paper. Okay, so in this chart right here, the left-hand side is analyzing f of x and its graph. So that's the generic function up here that we're going to be analyzing. That's generic. And then on the right side right here, we'll actually use this p of x right here. We'll use this function to say like, okay, for this example, this is what we mean. All right, so the degree, if you look at here, the degree, this is the first term, right? And it's written in standard form. The degree would be the highest exponents. That's n right there. The degree of this polynomial is the highest exponent, which is this 3 right here. All right, next we're going to talk about zeros, x-intercepts, roots, solutions. So it may be necessary to factor f first. So to find zeros, we already know how to do this. We did this in your summer packet. We did this on your first quiz. We did this on our last test. So find zeros by setting y equal to 0 and solving. So set the function, we'll say, instead of y, because it can be named anything you want, equal to 0 and solving. So here are a few important things to know. If f of r is 0, then r is a real number, then, so if it's saying if you plug in 3 or whatever, 2, 6, -5, and you get 0, and that's the number that I just said is a real number, then x equals that number as a solution. So x equals, let's just call r 3 for a second. X equals 3 as a solution. I shouldn't say 3 because this is 3. Let's say 2. X equals 2 as a solution. 2 is also called a 0. 2, 0 is an x-intercept. And then x minus 2 is a factor. Also, if x minus 2 or x minus r occurs more than once, then it's called a repeated 0. So to properly understand what I was just trying to say right there, let's just find the zeros, x-intercepts, and factors. Okay, to find the zeros, once again, you're going to set your function equal to 0 and solve. So 0 equals x cubed plus 4x squared plus 4x. All right, now I need to solve this. Remember, if you're ever saying to yourself, wait, how do you solve a cubic function again, or a quartic, or a quintic, or whatever degree polynomial? The answer is that you have to try to factor it, okay? This is already equal to 0, so now I'm going to look for GCF. There is a GCF, which is x, and then I have x squared plus 4x plus 4. And now I can factor what's left. So I have 0 equals x times, and then this factors to x plus 2 times x plus 2. You could also write this as 0 equals x times x plus 2 quantity squared, right? That's the same thing. All right, zeros, we're going to find our zeros by setting each factor equal to 0 and solving. So I'm going to set this equal to 0 and solve, this equal to 0 and solve, and this equal to 0 and solve. So I have x equals 0 and x equals -2. Those are my zeros. Now I'm going to find my x-intercepts. I already found my x-intercepts. I just have to write them as ordered pairs. So I have 0, 0, and -2, 0. When I plugged in 0 for y, I got 0 for x. When I plugged in 0 for y, I also got -2 for x. And then finally, there's our factors. Okay, so our factors were x, and then x plus 2, and there's 2 of them. And there's only one of these if you really want to get crazy here. Okay, so next we're going to talk about the multiplicity. The multiplicity, you really just have to look, okay? So if your factor is raised to a power, okay, and so like let's just read through this first. It says if x minus r to the m is a factor of f and m is the largest possible power of x minus r, then r has a multiplicity m. Zeros of even multiplicity, with the even multiplicity, if m is even, then that means that if that factor occurs more than once and it occurs an even amount of times, something special is going to happen with the graph. Okay, so let me refer to our factors here. This factor is happening an even amount of times. If it's happening an even amount of times, what's going to happen is that your graph is going to touch the x-axis. A lot of times people say bounce. I don't care either one's fine. It's either going to touch, bounce off the x-axis. So if this was the x-axis, it'd go like that. Okay. If it appears an odd number of times, like this right here, that's an odd number of times, then the graph will cross the x-axis. So it says, does the graph touch or cross the x-axis at each 0? So we have a 0 at 0, and we had a 0 at -2. So let's say what happens at each one. So at 0, if you look, the multiplicity is 1. So that means that it has odd multiplicity, and that means that it is going to cross the x-axis at 0. Okay. If you look at -2, where it came from is this factor, it has an even multiplicity. So that means it's going to touch the x-axis there. It's going to bounce off of it instead of crossing it. Okay. Next part, it says a polynomial function has at most n distinct real zeros. So if the degree, like on the last one, has a degree of, or the polynomial has a degree of 3, that means at most we're going to get 3 zeros. It could have 2 zeros, it could have 1 0, but it couldn't have 4 zeros. The number of turning points at most. So it doesn't mean it has to do it that many times, but it's going to have at most n minus 1 turns. So our third degree polynomial could only turn a possible of 2 times. It couldn't turn more than 2. It could turn less than 2 times, but no more than 2. Okay, so what we have left here are just examples of functions that we would graph in class. Okay, so first off, let's start off by getting the degree. In order to find the degree, it has to be written in standard form. So let's go through these really quickly, all 4 of them, and look at them and see if they're in standard form. This is in standard form. It has its 3 terms, meaning when I look at it, if it's factored, it's not in standard form. It would have to be multiplied out. So that's in standard form. This is also in standard form. If you look at the last 2, these are not in standard form. So I can't look at it and say, oh, the degree is blank. I would have to think about expanding it in order to do that. Okay, so let's start with this first one here. The degree, it's in standard form, so I can look to see using the first term test what the degree is. The degree is 3. The lead coefficient's -2. I can also do end behavior right now. So I can say the limit as x approaches -infinity of the function g of x is. And now I can use my leading term test to decide what this looks like here. The degree is 3, so my arrows are pointing in opposite directions, and the lead coefficient's -2, so that would be like a negative slope line. So the limit as x approaches -infinity is positive infinity. The limit as x approaches positive infinity of my function g of x is, as you look, your y values are decreasing, so that's -infinity. The number of real zeros, the possible number of zeros here is going to be the same as the degree, which is 3. The y-intercept, I know how to find that. I plug in 0 for x and see what I get for y. So I'm going to plug in 0 for x here. -2 times 0 cubed minus 4 times 0 squared plus 16 times 0 is 0. X-intercepts, if any. So remember, x-intercepts and zeros have the same answers. They're just written 2 different ways. So I'm going to do all the math off to the side for that. So I'll find my zeros first. So I have 0 equals -2x cubed minus 4x squared plus 16x. And now I need to solve this. Remember, to solve this, I'm going to need to factor it. So it looks like all my 3 of my terms have an x in common, but they're also even, so I can factor out a 2. But my lead coefficient's also negative. So I'm going to factor a -2x out of all 3 of those. So if I do that, I have x squared plus 2x minus 8. Now I'm going to factor that. So I have x plus 4 and x minus 2 still left there. And now I can get my 3 zeros. So in this case, I have 3 zeros because I can set this equal to 0, this equal to 0, and this equal to 0, and solve each one for x. So I get x equals 0, x equals -4, and x equals 2. That means I have 3 x-intercepts also. 0, 0, -4, 0, and 2, 0. Okay, in this part right here, it says I also want to know the multiplicity. So multiplicity, you're going to use the word either even or odd. You need to look at the factors for that. So here are my factors. There's one factor here, one factor here, one factor here. So all three of these are odd. That means that at all three of them, I'm going to cross the x-axis. Number of turning points possibly is one less than the degree. So this would at most turn 2 times. All right, that's it for our first example. Why don't you pause the video and try the next one on your own and just compare it with mine. All right, it's already in standard form, so the degree is 5. The lead coefficient's 3. 5 is odd, so my arrows are going to be pointing in opposite directions. 3 is positive, so it would look like that. So I can do my end behavior now. The limit as x approaches negative infinity of my function, this time is called f of x, is, as my x values get smaller, so do my y values. The limit as x approaches infinity of my function f of x is, as my x values get bigger, so do my y values. At most, there will be 5 zeros here. Remember, it's at most, so there could be 4. There could be 3, 2, 1. My y-intercept I'm going to get by plugging in 0 for x. 0 to the 5th is 0, 0 to the 4th is 0, 0 cubed is 0, so this is going to be 0. It's not always 0, 0, just on this last two they have been. All right, I'm going to find my zeros, so I'm going to set my function equal to 0 and solve. 0 equals 3x to the 5th minus 18x to the 4th plus 27x cubed. Okay, so this time they all have a 3 in common, and they all have an x cubed in common. So now I have x squared minus 6x plus 9. And then I have 0 equals 3x cubed times. And then I need two numbers that multiply to give me 9 and add to give me negative 6, which is negative 3 and negative 3. So I have x minus 3 twice. Okay. Now I can write my zeros. I'm going to set each factor equal to 0 and solve. So if I set this equal to 0, if I set that equal to 0 and that equal to 0, I get x equals 0 and x equals 3. That means I have two x-intercepts, 0, 0, and 3, 0. Now I can state the multiplicity. Okay, I look at this one here. That's odd. I look at this one here, that's even. So here it's going to cross the x-axis, here it's going to touch the x-axis. Number of turning points, at most there will be 4. There could be less than that though. So notice also right here I said at most I was going to get 5 zeros and I only got 2. You won't necessarily get 5, it's just saying that there would be no more than 5. Okay, the next two are similar because if you look at them, oops, they are both factored already. So the good news is that this part, you don't have to do that work. It's already done there for you. But you don't see what your first term is. So I have to expand this. Now, I could say I have to expand the whole entire thing, and that would take me, oh gosh, so long. But instead, I'm just going to figure out what the first term would be. So I'm going to do 1/2 times x to the 3rd times x to the 4th. And I can figure out what my first term would be. So I know it's going to be 1/2. So I'll get p of x equals 1/2 x to the, so this is first power times 3rd times 4th is 8th power. Then I get plus, whatever. Okay, but you only need to know the first term. So the degree is 8. The lead coefficient is 1/2, and then my end behavior, the limit as x approaches negative infinity of this function, which is p of x, is. So now I look at this one here and I say, okay, what's going on here? So 8 is even, so my arrows are pointing in the same direction. 1/2 is positive, so it looks like that. So both my end behaviors, I'm going to say that they're approaching positive infinity. Limit as x approaches infinity of p of x is positive infinity. At most, there will be 8 zeros. So notice if it's factored, you can't see the degree. Okay, if it's factored, you can't see the degree. If it is not factored, you can see the degree. So the most common mistake people make is that they'll start adding these to get the degree. That's not factored. You only have to do that if it's factored. Okay, y-intercept. Plug in 0 for x and see what you get for y. So I'm going to do that math off to the side here. I have 1/2 times, I got to plug in 0 there, there, and there. All right, so 0 minus 1 is -1. 0 minus 3 is -3, and then I have to cube it, which is -27. 0 plus 2 is 2. 2 to the 4th power is 16. All right, so this is a positive times a negative times a negative times a positive, which is a positive number. Then I'm going to do 1/2 times 16, which is 8. So I got rid of those now. And now I have to do 8 times 27. So I'm going to do 27 times 8. 6, carry the 5, 16, 216. So my y-intercept is 0, 216. My x-intercepts, I set my factors equal to 0 and solve. So the good news is this part's going to be done pretty quickly here. So I'm going to set each factor equal to 0 and solve. So I'm going to set 1/2 equal to 0 and solve for x. There is no x, so there I don't have to do that one. I'm going to set this equal to 0 and solve, and I get 1. So x equals 1 is my first 0. Now I'm going to set this equal to 0 and solve. I get 3. So x equals 3 is my second 0. X equals -2 is my third 0. So I have 3 x-intercepts, 1, 0, 3, 0, and -2, 0. Okay, if this was 1/2 x, then you'd also have a 0 at 0, but it's not. Okay. Now I want to know the multiplicity, so I'm going to look at each of the multiplicities. So this is 1, so that's odd. This is 3, so that's odd. So the first two are odd, so I'm going to go like this to save myself some time. Odd. So here it's going to cross. This one comes from this degree, this exponent, so it's even. So it's going to touch there. Number of turning points, 1 less than the degree, so 7. All right, go ahead and pause the video and try the last one on your own, and then just come back and check your answers with me. All right, I can't tell by looking at it what the degree is because I don't know what the first term is because this is factored. So let's figure out the first term is q of x equals, I have 2x squared, and then I'm going to multiply that by x squared, which is -2. I accidentally said 2. -2x to the 4th, and then I'm going to have something after that. All right, so my degree is 4. My lead coefficient's -2. The limit as x approaches -infinity of my function, which is q of x is. Same direction, both pointing downward, so -infinity. Limit as x approaches infinity of q of x is -infinity also. Number of real zeros at most is the same as the degree, so 4. Y-intercept, 0, comma. I need to plug in 0 for x and see what I get for y. So if I plug in 0 here, I get 0 there, times 0 minus 4 is -4 squared is 16. And it doesn't matter what I got here because I got 0 here. So it's 0, 0. X-intercept, set each factor equal to 0 and solve. So I'm going to set this factor equal to 0 and this factor equal to 0. So if I set the first factor equal to 0, I get x equals 0. My second factor, I get x equals 4. So I have 0, 0, and 4, 0. Multiplicity, this is a 2 and a 2, so they're both even. That means I'm going to touch at both of them. Last but not least, the number of turning points, 1 less than the degree, so at most it'll turn 3 times. All right, that's it for the notes for 2-2 day 1. Now we're going to do 2